Hello, everyone. Welcome to our Waterhackweek 2020 Cyberseminar series. My name is Julia Masterman. I am the Education and Outreach Coordinator here at Quasi. While everyone's getting logged on, just some logistical information for this webinar. This webinar will be recorded and posted on the Quasi website afterwards. Please enter any questions that you have throughout the presentation in the question and answer box within Zoom. Our panelists will have the opportunity to answer them throughout the seminar, and hopefully we can have some great discussion. Once again, thank you for tuning in to this fourth installment of the 2020 Waterhackweek seminar series. And with that, I'm going to pass it off to Emilio, who can introduce himself, and we can get started. Emilio?
Yes, so let's just testing. Will I be asking you to advance slides? It looks like I don't have a... will you be advancing the slides rather than me? I don't have a... Hello? Hello?
Sorry, I muted myself. Yes,
okay.
I can advance the slides.
Okay. Oh, hi, I'm Emilio Mayorga. I'm a research scientist at the Applied Physics Lab at the University of Washington in Seattle. I hail from biogeochemistry and oceanography, but these days I work mostly on data systems and involving water, both salty and freshwater. Next slide, please. As Julia just said, we encourage you to send any questions or comments all throughout the seminar via Slack or the Zoom chat. If you've attended the seminars before, hopefully you've interacted with Slack already, and hopefully you are on Slack already. We'll be monitoring both, so please chime in. Next slide. Okay. This week we'll be talking about modeling and big compute. You may remember that last week the topic was on interactive coding and on the web, especially in the web, but it could be local also. So in a sense, we are expanding that or building on that topic this time. Next slide. Well, just to get things started, this is not my own area of expertise, so I'm coming at this probably from the same place as many of you. I have done modeling in the past, but never on a high-performance computing or the cloud, per se. So our panelists are experts at this, and I just wanted to set the stage, if you will. Hopefully some of these questions will resonate with you. I start with my model, and maybe it's a model code that is a community code, but I still run it on my server. It's just become too big. I started running it on my little watershed, and now I want to do the whole US. And it's just too big for my laptop or my group server. So what do I do now? We come from a range of ages, and I remember people still, I don't know if people still talk about supercomputers. I haven't heard the term in a while. Are HPCs the what used to be called supercomputers? What is the difference? I hear about Exceed, Jetstream, Stampede, Pleiades. What's what? Are they all HPCs? Can I have one? How do I have one? Should I want one? Do I have to rewrite my code to do all of that? Whatever happened to MPI for parallelization? I remember hearing about that. Is that out the window, or is it still relevant? Or do we scrap all of that and just the cloud is the answer for big modeling? And Pingeo will solve all the problems. You'll be hearing from Anand about Exceed and Joe first about Pingeo. Or is Pingeo just too confusing, or do I just sign up and get my account with one of the big three, Amazon, Google, and Azure? How about Jupyter Hub? Is that how we run our models now? But which one? Hydroshare, Systems, Pingeo, some others? Well, as you can see, my head is ready to explode. But hopefully, everything will be resolved by the end of the hour, both from the panelists' presentations, but also from your input. and you'll set me straight. Next slide, please. Yes, so it'll all be good by the end, and we'll be on our way to do productive science with big models. Next slide. Our first speaker, our panelist, is Joe Hammond. He's a project scientist at NCAR. Well, NCAR is in Boulder, but Joe is physically based here in Seattle. He will be talking about Pingeo, definitely modeling on big compute of all sorts. The next panelist will be Anand Padmanabhan, a senior research scientist at the Cyber Infrastructure and Geospatial Information Lab at the University of Illinois, or at Urbana-Champaign at an NCSA, and he'll be talking about Exceed and HPCs. And then we'll have facilitated conversations about HydroShare tutorials, especially focused on models on HydroShare. And next slide, and we'll turn it over to, oh, no, not just yet, to motivate discussions. We've asked our panelists, and we asked you to consider. I apologize, these considerations are rather long, but maybe they reflect some of the confusion I was mentioning before. Like what do we do if we start with a model, or at least the running of the model in a smallish environment? And do I just transport it to an HPC or the cloud easily? Are these three my local servers, HPC and commercial cloud? Is it easy to go from one to the other? Or it's just too hard and time consuming to port our models and data from one to the other, especially if our models are extra tricky. So those are supposed to be provocative statements. I don't know the answer. I don't know that there is one answer, but I want to hear from the panelists. Over the last 40 years, our community has shifted. In a sense, you could almost say back and forth from big centralized mainframes to decentralized computing. And now we are, in some ways, re-centralizing again in a different kind of centralization. As data becomes larger and as the capabilities of existing HPCs and the commercial cloud have become fantastic. So what should the computing environment for our scientists look like in 2030? Where should we go? Also, lab scientists, as some of us know, at least lab and field scientists spend a significant amount of time as part of their education just learning proper lab techniques and documentation. In computational or earth science, people come from different backgrounds. Much less formal effort is spent acquiring analogous computing skills that support proper coding and reproducibility. I think we all experience that. So what can we do as a community to change this? Or if we're doing some of that well, how can we expand that? Next. And I'll turn it over to our first panelist, Joe Hammond. Take it away, Joe.
Great. Can you hear me? Yes, you can hear me?
Yep.
Okay, good. So hi, everyone. Like Emilio said, my name is Joe Hammond. I'm a project scientist at the National Center for Atmospheric Research in the Climate and Global Dynamics Lab, where my work focuses at the intersection of hydrology, climate, and data science and big data science. So I want to first welcome us all to the big data era, and I want to tell you a little bit about how what I mean by that. So on this slide, I have I'm showing two examples of data archives that are commonly used in the environmental sciences. The first is the CMIP archive. This is the Coupled Model Intercomparison Climate Model Dataset Archive. And there have been now 5 iterations of CMIP, CMIP 2, 3, 5, and 6. And CMIP 6 is just becoming available now. It's being produced by about 30 modeling centers around the world. And these are simulation models that give us a kind of the best representation of how the climate will respond to increased carbon emissions here on Earth. It's a wildly popular data set, and it's also really large. And so the bar graph that I'm showing here is the size of the CMIP archive, each iteration of the CMIP archive. So CMIP 5, which came out about 7 years ago, was about 3.3 petabytes. And CMIP 6 is looking to be about 10 times larger than that. So the estimated archive size right now is looking like it's going to be upwards of 20 petabytes. So in just the CMIP side, this is just one data set. We're starting to look at really large quantities of data. On the observation side, on the right side of my screen here, I'm showing a slide showing portraying all of the NASA satellites that have existed to date. And some of these you'll recognize, and some of them are a little more obscure. But these are just the satellites NASA has launched for Earth science missions. The chart in the bottom right corner is showing the growth of the NASA Earth Data Science archive from 2015 and then projecting out to 2025. The y-axis here is in petabytes, and what it's showing you is that by 2025, NASA is expecting somewhere between 250 and actually, in some estimates, up to 300 petabytes of data that they'll be storing in their archive. And of course, these are really valuable resources, but this presents some interesting challenges to the end user of these data sets in terms of how do we actually work with and manage our science applications in the face of such large quantities of data. So you can go to the next slide. Okay, so what science do we do, or do we want to do with our big data? So one thing we do, you can flip through all these just kind of one at a time. One thing we want to do is we want to take the mean. We may want to analyze the variability, so take the standard deviation across a large ensemble of data sets, or maybe we want to do machine learning. And the question is, like, what do all these sorts of operations have in common? And I think the best answer here is that they need all of the data. So in all three of these examples, to build these examples, to either train a machine learning model or to calculate the ensemble mean or the ensemble standard deviation, I needed the full set of model simulations to do that. And so we need all the data. We can't just access the data over, say, Colorado to calculate any of these, to do any of these scientific studies or to calculate any of these quantities. So we need all the data. But the data is, say, 20 petabytes in volume. How are we going to do that? Next slide. Okay, so there's a bunch of models that have been put forward. These are kind of in broad brushstrokes, models for working with big data. So the status quo approach, and one that we're all familiar with at one level or another, is the file-based approach. So here we go to some data archive. Maybe this is the Earth System Grid Federation. Maybe this is some other data provider. Maybe this is the NASA DAX. And we download our files. We use some API that they provide for downloading, for discovering and downloading the data. And we download those and we put those on our hard drives. Maybe we have a stack of hard drives we keep on our desk, and we plug our laptop into those or our desktop, and we do our analysis there. And this is nice. We can obviously control the software environment on our computer, and it works pretty well for small data. When we move to big data, this system starts to break down. Okay, so maybe we try a database or an API approach, a service that stores our data for us and gives us some API or some application programming interface, some like scripted set of tools that I can operate on this archive that is managed by this service. So a really good example of this is Google Earth Engine. Google Earth Engine has a ton of data that they provide that's stored inside of Google Earth Engine. And then they have an API built on top of that that allows you to do a selection of GIS-like operations on that data. Of course, the downsides to using a database are that you don't control the data. It may be hard to add additional data to that archive, and you don't control the computational environment. It's often difficult in these systems to go, as we say, off-roading with a service approach, because the types of operations that are supported are really highly optimized for the way the data is stored. And so while the database API approach or service approach can be really useful for certain applications, we find that it has its limits in terms of how far you can take it. All right, the final approach that I wanted to talk about, and where we've been spending a lot of our time on the Pingeo project, is the cloud approach. So here we take a bit of a different architecture where we co-locate data and compute in the cloud, and then we federate access to both of those through well-established cloud practices. So we put our data in object store that has a global namespace, and it can be referenced from anywhere inside the cloud or outside the cloud. And then we access the cloud and its computational environments through some thin interface. And on the next slide, I'm going to show you kind of what that looks like in a more tangible sense. You can advance. In 2 slides. I'm going to first tell you about the Pingeo project. So Pingeo is 3 things. It's kind of overarching idea is that it's a community effort for big data geoscience applications. Inside the Pingeo project, there are kind of 3 main topical ideas. The first is that Pingeo is a community that works together to promote open, reproducible, and scalable science. So the community is made up of scientists and software engineers and infrastructure providers that work together in an open source, open science framework. The second is that Pingeo is an integrated ecosystem of open source software tools. So here the focus is on the scientific Python ecosystem, which I'm showing in this middle figure on the left. We work a lot in particular with the Jupyter, Xarray, and Dask projects. But the really cool thing about the Python ecosystem is that interoperability is kind of baked into the way a lot of these tools work. And so there's a lot of flexibility in how you compose the type of environment that you work in. And then finally, Pingeo is a community platform. And so the platform we've been building is built on Jupyter Hub, and we've deployed various Jupyter Hubs. So Jupyter Hub is a multi-user gateway to Jupyter notebooks. So we've deployed these on all the cloud providers. They can Pingeo Jupyter Hubs can be deployed on Jetstream or on local hardware like a compute cluster in your lab or on an HPC system. And then co-located with these hubs is cloud optimized data. So we have a catalog of data that's available on the cloud, either in AWS or in Google or in Azure. And then there are these highly configurable software and hardware environments. And so I gave one example here, which is a binder hub, which allows you to take a GitHub repository of Jupyter notebooks and launch that GitHub repository directly on the cloud. But so when you put all 3 of these together, the Jupyter Hub, the cloud data, and the configurable environment, you end up with this really flexible, powerful community platform. Next slide. So there's a wrong way. Go the other way. Thank you. Yeah, so this is just a quick snapshot of what this architecture looks like. We have some cloud or HPC system. That's what the center box is there. So maybe this is Google, one region of Google Cloud. And then we have these environments that I was talking about that allows us to take the open source scientific Python ecosystem, X-Ray and Dask in this example, and deploy those across the cluster. So Dask is a tool for parallel computing, and it allows us to scale computations that are either using NumPy or Pandas or Xarray. We can scale those computations across many computers. And those mini computers can all access what we refer to as analysis ready data. So this is data that's on distributed storage, and that can be accessed by all of the workers in a cluster. We use Jupyter as the thin client interface, or as the way to access these remote systems. And I think a lot of people on this call are probably familiar with Jupyter, but it's proving to be a really powerful interface to accessing these large compute systems. Rather than SSHing in and SCPing your files around Jupyter in the Jupyter ecosystem, provide a lot of tooling around how you access these remote systems. So that's the basic Pingeo architecture, and we have deployments of these Jupyter hubs with this set of tooling and these data in a bunch of places. So if you could go to the next slide. Oh, I have one more slide. Maybe we launched too soon. Can you refresh the slide deck? Yeah, thank you. So I'm not going to go through all these demos because my time is mostly up, but I thought I'd leave these here for a second and you can take a screenshot or you can quickly jot down the links. But here's two links to kind of demonstrate how this works. So the first is a GitHub repository that Freddie Kratzert put together demonstrating his machine learning application for hydrologic modeling. And so here you'll see a binder link in the README, and you click on that and it'll launch this notebook in a interactive Jupyter session. The same is true for Henri Drake's CMIP6 temperature analysis. And both of these are really nice examples of how you package up your analysis in a way that is shareable and then interactive for other people to come and take a look at. So I think I'll stop with that, and I think there'll be time for questions or more conversation later.
Thank you, Joe. We'll turn it over to Anand, and we'll have a discussion among panelists after Anand or after Christina.
Okay. Sounds good. Can you hear me?
Yep, we can hear you well.
Okay, great. Hi, this is Anand Padmanabhan. I'm a senior research scientist here at the University of Illinois at Urbana-Champaign, the CyberGS Center here, and with the National Center of Supercomputing Applications. And today I'll be talking mainly about the platform we have built for the HydroShare project called the CyberGS for Water. Here's a kind of a architecture diagram. You don't need to know about all the details, but basically this is in line with our previous speaker as well, who was talking about our Jetstream and allocations and Jupyter Hub. So here we have a Jupyter Hub based platform called CyberGS for Water, which we have deployed on Jetstream. The master node is on Jetstream, and then we have worker nodes which are on both Illinois and on Jetstream. So scaling between the cloud and local environments in order to run Jupyter, in order to run computational job on Jupyter. So this is based on Docker Swarm, and it can scale to a number of nodes. So next slide, please. So in this case, we are using two systems, which one is called the Roger or Virtual Roger here at Illinois, which is a supercomputer which was built for GIS-based applications. We are basically using the cloud portion of this for supporting the Jupyter instances or the Jupyter notebook. And then on the Exceed, which is um, the supercomputing centers put together. It's kind of a software. I'll talk a little bit about Exceed later, but it's an extreme science and engineering digital environment. That's what it stands for. Basically, a bunch of supercomputing centers which are offering high performance computing and cloud computing tools. And Jetstream is a cloud platform based on OpenStack, and so our Jupyter instances also run on Jetstream as well. Next slide, please. So one thing I'll demonstrate today is what we have built for a hydrological model called Summa. Many of you might know that model. So we have a Summa model which is configured, and we have PySumma, which is the Python version of it. You can run the Summa within the notebook, like you can maybe set everything up within the notebook. Then you can run an ensemble of models on an HPC environment, and then do some pre and post processing. So all this happens within that single Jupyter container, but then you are able to connect to an outside HPC or a high performance computing system. In the specific example, I'll show you how we are doing it with one of the Exceed system based in San Diego Supercomputing Center called Comet. So we connect to Comet, we run an ensemble of Summa models there, we get back the results. Hopefully we'll have time to see that. Next slide, please. Okay, and so every model has its binary as well as the executable and the model parameters and the data. So all these are packaged up into a Singularity container, and this is what is run on Exceed. So the container itself has all the compiled models and everything. So let's see an example. I think that would make it clear. So next slide. Can you go to that link, the first link? So these two links, one is a HydroShare resource, the first one, and the second one is the CyberGS for water. So those are the two links there. So if you go to the HydroShare resource, and of course you have to sign in, I believe. Sign in to HydroShare. I presume you should have an HydroShare account.
Yes, but it might be easier if you have the links open if you wanted to share your screen.
That's also okay. I think this should be doable for you as well. Let's test it, I guess. Should make it easy. But if not, I can always share my screens.
And I will post these links on Slack.
Okay, it's not letting me log in, so let's have you share your screen.
Okay, no worries.
So you should just be able to.
I should be able to do that. Let's see. Share. I think this is the correct one. If you see something not appropriate, let me know.
Looks good.
Okay, so you are seeing the model. So I think I'm logged in to HydroShare. So this is something any of you can do. So you have a HydroShare. So this is a model which is already created. So you can click on the Open With button, and you have a bunch of these things there. You can do a CyberGS Jupyter for water. That's the platform we have created. Just click on it, then it will open up. It will use your HydroShare account to directly log into this platform, so you don't need a separate account. I already have downloaded it, so I'll let it override it. So basically what's happening is it's going to the GitHub repository, it's downloading all the files needed, and then we have these models which we have created and the README. So let me look at the ensemble model, which is there. So this is the whole notebook. all of you might have seen notebooks before, so this is nothing new. But the key thing here is now I can run this notebook. I'm creating a pointing to a resource ID, which basically is this particular resource on HydroShare. It's a model essentially with which has been published. So we are taking a model which has been published as a resource ID. We are importing the model. So this is taking. Okay, so that's done. And so now we are unzipping this model. So it's doing that unzip. So there is, so this one is actually configuring the model to have the right paths there. So it's a, so the paths are correctly mentioned, so it can be executed. So that's once that's done, we can run the use Summa to build the ensemble models. So here we are building a bunch of ensemble models. So there are 75. So if you look at this code is basically generating 75 ensemble runs. So that's generated. And now we are using the library we have created in CyberGS to do the job submission to exceed. So in this case, we are saying how many, this is kind of an HPC parameters, how much runtime, 1 hour should be sufficient. I'll say we need 16 nodes since we are running 75 models at the same time, and we submit a job. So what is happening in the background is these jobs are being submitted to exceed. And you see this is SSHing into Comet machine, which is on exceed. And the job is in the queue system. Now, depending on how long it takes on exceed, this might be very quick or it might take a long time. So let's wait for a few seconds to see if it can start running the model. So you see the various status there, queue means it's queuing. So we are constantly querying that model to see what it's doing. And once it starts running, it should be fairly quick because these are like simple model runs, I think maybe a couple minutes being taken. But the nice thing here is with just like these 2 lines of code, the one which is 7 and 8 here, this is actually taking that number of models that we have, the ensemble models that we have configured in the Jupyter environment and actually running it on an exceed machine on a HPC. So that way you are bridging between your local environment as well as this Jupyter environment and the HPC environment in order to do computation. Now, that's one thing about HPC that I don't have control of what the queue time will be. But usually it's fast, but yeah, it could take long, depending on how many other users are using the system. So it's going to the batch system. So let's wait on this. I don't want to spend too much time on here, but I think hopefully once this starts running, I'll explain to you what the next steps are. You are getting the model outputs from HPC. We are just downloading the results there, and then we can plot some of the data within the Jupyter. This was kind of the runs which were previously done. Excuse me. Okay, so maybe we can come back to this. I don't want all of us to be just watching at it's queued up, but let's we can come back to this at a later time and see if it is running. So I'll go back to the slides maybe, and you can see this. So exceed, I talked about exceed. Exceed is basically a collection of advanced digital resources, meaning supercomputing resources, data resources, tools and expertise that are available to all researchers and scientists within the US. And you can see a list of resources. The one thing, great thing about exceed is you have a variety of resources. Now we were using Comet which was the HPC side. We have something like Stampede, which also provides SPC, and it has some Hadoop. And we have Bridges, which is more on a high performance, high memory kind of a system. It has a system which has a terabyte of memory, as well as it has, there is platform designed for AI, for visualization. So you have various types or modalities of computings which can be brought to for your problem. So various computing environments can be brought together. So you can look at the list of resources here on Exceed, and you should be able to see it, I think. So you see a large number of network storage and compute resources. So you have these various resources which are available on Exceed. Lastly, how do you get access to Exceed? There is a link here which tells you how to do an allocation for people who are starting out or doing education grants. There is a startup and education allocations which are much easier to get, and then there is of course a research allocation which is more peer reviewed, and it goes through a panel like any proposal. So it's kind of a proposal that you write. So let me come back to the ensemble model to see if there is any progress. If not, unfortunately, I guess the queue is busy, but if it were not, we would see it running, and then it completes the result, and then we get some outputs which we can look here.
Maybe we can come back to it and then later if it's still running.
Exactly.
Time.
Yep, that's okay.
Well, thank you,
So,
Anand.
yeah,
Oh,
I'll
sorry,
release the screen as well. So.
Oh, right. Okay. Christina, will you still be showing us or a quick demo of well, there you go. Take it away.
Yeah, we have since we have about 16 minutes left, what I thought we could do is I can show a few slides, but in this amount of time, as Anand has illustrated, it really does take some time to get familiar with working through workflows and accessing data and information. So we tried to give as much information as possible to people in advance of Waterhackweek so you can get comfortable with some of these workflows. So I've got some some tabs open where things have already run, but of course some things take time. I wanted to just take a pause for a moment and show or talk about sort of the map of options for accessing the cloud at Waterhackweek. So this picture is about, let's look at the white ladder in the middle. These are the tutorials. So one thing we've decided, or we know for sure, is that at Waterhackweek, we want as many people as possible to have as easy as possible access to running the tutorials that are going to be Jupyter notebooks that we're sharing with, especially during the morning. And so that workflow, we're going to make sure everybody knows how to do Monday morning. We're going to work through it. So if you don't have a lot of time before Waterhackweek to work through these workflows, that's fine, because Monday morning we're going to make sure everyone's on board and can use this quasi Jupyter hub as the access for all tutorials. Now, everything we're presenting to you is for anyone who wants to go beyond that, to access more cloud resources that you think could help advance your research. And some of those could be used in projects. So the project work that we do in the afternoon, your team could say, the Quasi Jupyter Hub has everything we need on it. We're set. Our project is going to be using that. So that's sort of plan A, and everyone will know how to use it. But if you have a bigger model, or you have another cloud option that you think you have experience with, or you think is going to be a better choice for your research project, or it's just something you want to get experience with it at Waterhackweek, we want you to have access and support to those options. So these other cloud options, like we've talked about Pingeo and Exceed today, and also ways to access other Jupyter hubs and commercial options. So those are the options, and the ladders are important to think about in the sense of scaffolding or ladders, or like the steps you take to be able to access these resources. In some cases, the ladders take a lot of steps, but the developers of those ladders to get to those platforms have already done the work for you. So that's the beauty of sort of the open source community and working together to share all of these tools with each other, is that in some cases, the developers have already done so much work that it really makes it easy. In other cases, you know, the innovation's happening and the ladders that need to be built to get to different platforms is part of our work at Waterhackweek. And so everyone contributing and having these experiences of getting access to these platforms and then navigating how to use those platforms for your research is very much a opportunity to learn and to work with developers and each other to make these platforms work for our research projects, so we're getting more science done. Does that, I hope that sort of overall picture of where all these technologies fit helps people understand how to interact with it. On the next slide, I'm going to go through these announcements and opportunities next, or I could do a quick run through on other, and then at the end we'll see how much time we have left to look at for an example of how easy it is to run the notebooks using the Quasi-Jupyter Hub server to access a model like LAN Lab. These learning activities that we've got outlined here are links so that you can read more about Pingeo and explore access to that. And you can also find information through, well, if you Google Pingeo, that's what I would say, but we're going to pass it back to ask more questions, address more questions to Anand and Joe in a minute. So all of these resources are here, especially these CMIP6 project resources might be of interest to people. And then the Exceed options, I'd also like to come out of this seminar with an idea of if people want to access Exceed or they want to access Pingeo during Waterhackweek, please let us know in Slack or in the chat so that we can put together a proposal to get an educational allocation for Exceed for people who want to use Exceed at Waterhackweek. And also with, you know, inviting Joe to join us at Waterhackweek or join your project at Waterhackweek, or to just, you know, best ways to operate or get information from the Pingeo team. And the next slide. Next week, we're going to work with people who use a lot of these cloud platforms for their work, because if you are scaling from field observations up to global climate change predictions, you've got a lot of computation that needs to happen. So we're going to talk about some of those challenges with Barney Sin and Yin-Fan Sang next week. They are both professors, but also Waterhackweek alumni and supporters of the community. Next slide. And the provocative piece about next week, just as an introduction, is that it's great to scale from field scale data to climate change predictions, but it's really difficult to scale to humans. And so the field of Geo Health and some experts that we've invited to join us, hopefully will just extend the conversation a bit into the Geo Health world. And we've got people coming to Waterhackweek who are interested in health topics and connecting all of our work and our research impacts. So next, quickly before we pass it back to panelists and look at more questions, I wanted to just propose this slide. I'm going to copy this slide over and the picture over into the Canary Opera channel that's in the Slack for Waterhackweek. And I just wanted to, you know, before we start asking questions, or just encourage you to ask more questions to Anand and Joe, some people might be feeling uncomfortable with all of the technology and information. What exactly do I do with all of these options? And that is the type of discomfort that we actually want you to try to be okay with when you're at Waterhackweek. And that experience discomfort is not any sort of sense of, physically we want everyone to feel safe, but we also mentally we want you to be okay with feeling challenged. And so one way that I think about this is a framing of the cognitive dissonance, right? You've got your workflows, your ways that you do research. You might be uncomfortable with new ways of doing your research with all of these cloud options and technology you might not be familiar with. So when you have that feeling, or if you're having that feeling after listening to Anand and Joe, one option is to just to respond like, great, I'm really uncomfortable right now. And I think my brain is like building new connections about how to do this. And that's exciting. Often people respond to feeling like they don't belong here, or I can't do this is too complicated. And then you could choose to not try, or to leave the situation, or to not use that technology. So that's a type of experience discomfort. What that means is maybe something that people could be feeling right now, and we want you to feel like that's normal. On the next slide, we are this LAN Lab modeling framework and use cases is something that we've done in last year and recorded in this Cyberseminar series from last year. So I'm going to add that link into the Slack channel and the chat, and then focus in our last few minutes on questions for Joe in Hammond. Next slide. I think, we did not repeat the slides with the questions. We have our slide. Could we go to the slide that has the provocative questions? Sorry about that. Yes. So, Joe, I have a question for you about how much time you spent on putting models and data together at the beginning of your work as a hydrologist, circa your master's degree, and how that contributed to your your efforts towards building environments that make all of this easier.
And that's a question for the panelists, I assume.
Yeah, is Joe still here?
Yeah, I'm still here. Can you maybe repeat the question one more time?
Well, so it's when you've got a model and you're developing your research with the workflow that works on your desktop or on your university server, it's time consuming to move things around. And what I wanted to know is, when you look at the environment that you started your master's degree in, compared, those experiences, like what about that experience led you to investing so much time in creating environments that make model and data transfer and mobility and interoperability easier for the rest of us, I guess I should say.
Sure. Yeah, so both my PhD research and my master's research involved running various large computational models. And associated with those models was this kind of suite of tools that we used for analysis, pre and post processing of the data, et cetera, et cetera. And what I noticed, and I think a lot of people have noticed this in recent years, is that those tools was where we were spending a lot of our time, and it was really hard to build systems that were extensible and easy to share. So we ended up just repeating ourselves a lot, and that just felt to me like something that I didn't want to keep seeing myself doing, kind of the same set of tasks over and over again. So the way I ended up getting started in this was working on the X-ray project. So as a first-year PhD student, I started working on that project, largely to help support the type of analysis I was doing on the climate model I was working on. But what I found was that by working on that tool, I was able to push a lot of the type of functionality that I would have otherwise been building just for myself. I was able to push that to a package that other people could use. Obviously, since then, that X-ray package has gained a lot of adoption. But in the early days, it was just a place for me to share the type of model analysis tools that I was building. Anyways.
So what I'm wondering is, for building on what Joe said, or that experience in hydrology and in hydrologic modeling that some of us have had, and which has led us to spending a lot of time on the software and technology side of computational frameworks or linking to cloud or HPC. How does that compare to other fields of science? So in your work with Exceed, how, like, are we alone in this, or are geo and earth scientists sort of learning from other people?
Yeah, I think that's a very good question. Definitely, you guys are not alone in this in terms of water or geo or hydro as such. Physics, biology, by all means, I guess physicists have been probably ahead of the curve, and they have been using these kinds of technology for their models, their simulations for a while, especially on HPC kind of environment and high throughput environments. But I think geo and hydro community have been catching up and are kind of increasingly using these resources. From my perspective, on Exceed, I see a number of projects um, that are using these and that are requesting help from the Exceed community in order to solve these problems. So yeah, I think it's been growing.
So I think so as a final question, since we're at time, I wanted to ask both of you, Joe and then Anand, who do you know of, or like a project that you know of, and it could be your own, that is got the best code hygiene, or like are the most reproducible, or the folks that are just, really spend a lot of time on it and really good at it, or somehow made it simple, that you think will lead to, like, that leads to your expectation of this is how we'll be doing computing in 2030? Does that make sense? So like the biggest hero you know now at the frontier of sorting all of this out, and then where you think they'll be by 2030.
Anand, you can go first.
Yeah, that's a very simple question, right? Yeah, I don't know if there is a answer, like if I can say if anyone does best, but there are like communities which have good practices which have been developed over time, like where their models are all on GitHub and their community has a shared platform for moving data. They have a common repository. I think HydroShare is a good example of where hydrology is moving to, in terms of having the data in a common environment. But other communities, especially physics, has done a lot in this domain, and in terms of reproducibility and replicability.
I'm really going to push you on this, Anand. Like, is there a research group then? Like, who is that group or that community that we could like go Google right now and say like, oh, those biologists that do forestry modeling in R, their ecology models are very well, like that is the best hygiene with code and software and community reproducibility that I know of,
Yeah, I don't know if I can answer that in terms of giving a particular group. I'll have to look up some groups. I know there are few in physics, high energy physics in particular, CMS and Atlas, which I've worked with. They have relatively good practice, but if do I know if they are the best around? I don't know.
Okay, that's true. We'd have to actually do a formal review. I understand you're giving a scientist type answer here. So with that disclaimer that we've not done formal review, Joe, do you have any like heroes of
Yeah, I have 2 or 3 examples that I would probably reach to. I think the AstroPy project, this is a Python project around astronomy, has been a kind of mainstay in this area, thinking about how to build an ecosystem of interoperable tools for astronomy. And so I think it's a nice example of how a community has been able to foster the development of a single package that meets the needs of a pretty broad range of astronomers. So that's one example. I put the link in there. The second in the R space is the R OpenSci community. This is not a community that I've been involved with directly. I'm more aware of what PyOpenSci is doing. So this isn't necessarily one specific domain, scientific domain, but it's more a community of practice around the types of tools that are being used. And these come with kind of best practices for how to package, document your code, how to support code citation and testing and that sort of thing. I see somebody here put NetPy in. I think NetPy is another good example. They've built a nice community around doing kind of classic meteorology with Python, and
yeah, I just added that.
That's been useful.
Yeah, I just added that because I met NetPy software library leader that's got. I really like their tutorials and their onboarding process. So like, here's how you do Python, and here's some starter tutorials, and it's really well set up. I think the link to what I like about HydroShare is that you first go to the tutorial and it's linked directly to the cloud resource to interact with the code is nice. But I'll put the hyperlinks to some of those that I put in there. Emilio, did you have any other comments or questions before?
No, I think we're good, and we're also 4 minutes past our time, or 5.
We started 5 minutes late, so thank you everyone for your patience. And do any final slides, Julia?
Sorry, could you repeat that?
So could we go to the next slides? For at the end, I think we just wanted to thank our sponsors and NSF, and we've got links to webinars from last year that step you through a lot of these options, and we're going to add these links, and everything in the chat is going to get transported over to the Slack channel for Cyberseminars. And if you want to interact more after the Cyberseminar, there is a place to do it. So thank you so much, Joe and Anand, for giving us all of your resources and perspectives on all of this. And thank you everyone for joining.
Thank you, Christina.
Thank you.
Thanks, Emilio. Thanks, Julia.
Thanks,
Thank
Christina.
you.